In this video, we are going to derive an equation we can use to solve one-dimensional elastic collision problems. Let's say we have a frictionless surface. Two objects m1 and m2 with initial velocities v1i and v2i collide with each other elastically. And we want to find their velocities immediately after the elastic collision. Because the two blocks do not stick together, they get different velocities v1f and v2f after the collision. This means we have two unknowns to find, so we need two equations. We know that we can use conservation of momentum for all collision problems. And because this particular collision is elastic, we can also have the conservation of kinetic energy. So this will give us two equations for our two unknowns. To write the initial momentum equals to final momentum, let's see. Initially, we have mv of the first block plus the mv of the second block. And afterwards, I have the mv of the first block plus the mv of the second block. So that's the conservation of momentum equation. And then for the kinetic energy, it's just like that one. It'll be 1/2 mv squared instead, of course. So 1/2 mv squared plus 1/2 mv squared equals to the 1/2 mv squared plus the 1/2 mv squared. So two equations. We can certainly solve for our two unknowns as long as the masses are given and the initial velocities are given. The only problem is this equation is a second-degree equation, so most likely we'll have to deal with quadratic equations. It would be nice if we don't have to deal with quadratic equations. So what we're going to do is we're going to derive a simpler equation to use instead. To derive that simpler equation, it's going to take us a little while. First, I'm going to cancel the 1/2. And then I'm going to move the m1 terms to the left side and the m2 terms to the right side. So if I move this one over, I can factor the m1 out. So this one is v1i squared. That one moved over here is going to become minus v1f squared. And then I'm going to move this term to the right side, and I can factor out the m2. So this will give me v2f squared. When I move this one over, it will be minus. So be minus v2i squared. And I'm going to do the same thing to this momentum equation. So this one, I'm going to move m1 term to the left side. So be m1 being factored out, and there will be v1i minus v1f. And move the m2 term to the other side, factor out the m2, and I'm left with v2f minus v2i. And then what I'm going to do is I'm going to divide this equation by that one. So this divided by that. And you can see the m1s will be canceled, m2s will cancel. And what do you think this will give us? This is like x squared minus y squared divided by x minus y. If you remember from your algebra class, you may have learned this. X squared minus y squared equals to x minus y times x plus y. So x squared minus y squared divided by x minus y would equal to x plus y. So with the m1s canceled, this part will equal to x plus y. So this will become x plus y v1i plus v1f equals to, on this side, this divided by that, m2 cancels also, and this becomes x plus y as well, will be v2f plus v2i. We're almost there. the next thing I'm going to do is I'm going to move the initial term back to the left side and the final term to the right side. So I'm going to get V1I minus V2I equals to V2F minus V1F. And this is the velocity difference between the two blocks before the collision. And the velocity difference, if you remember, it is also the relative velocity. So this is the relative velocity between the two blocks before the collision. This is the relative velocity between the two blocks after the collision. Now in this case here, this difference gives us something I would call approaching speed. Because before the collision, in order for the two blocks to collide, they'll have to approach each other. They have to get closer and closer so that they can collide. After the collision, because they have to separate, they do not stick together, so the relative velocity over here gives us the separating speed, the rate at which the two blocks gets farther and farther apart from each other. See, before the collision, in order for them to collide, if I use to the right as positive, that means the block behind has to have a more positive velocity. Or in this case, I'm just going to say faster. The block in the back must have a faster speed so they can catch up with the block in the front and then collide. So that's why before the collision, we're using V1I minus V2I. After the collision, they have to separate. That means the block in the front has to be faster. I mean, it's not necessarily faster. It just has to have a more positive velocity. That way, this one can get away from the block behind it. So afterwards, it is V2 minus V1, just because M2 has to be faster. This one has to have a more positive velocity before the collision. That one has to have a more positive velocity after the collision. And this here tells us that at whatever rate the block behind approaches the block in the front, the block in the front would separate at exactly the same rate from the block behind after the collision. So this approaching speed equals to the separating speed. So we get a new equation to use, but we still need two equations to solve our two unknowns. That means we can still use one of these two. Which one of these two do you think you will use? Of course, we'll use the momentum conservation, because the reason why we spent all that effort to derive this equation is because we want to avoid the quadratic equation. So we'll be using this one and the momentum conservation for one-dimensional elastic collision problems. And we will work on some examples in the next videos. For elastic collisions, I'm attaching a blade to one glider and a stretched rubber band to another glider. So when they collide, the blade will push into the rubber band and then bounces off. This will make the collisions between these two gliders very close to elastic. I have also added some weights onto the second glider, so it is heavier than the first glider. There are also stretched rubber bands at the two ends of the track. Let me turn on the pump. If the two gliders travel in the same direction before collision, the one in the back must be faster so it can catch up with the other glider and collide. I can also make them travel towards each other before collision. As you can see, no matter what, before the collision, they have to approach each other so they can collide. together, they must separate and get farther and farther away from each other.